Yeah, hello. I'm glad you're interested in that weird topic. My name is Anna. I like to talk about computer games, role-playing games, and theoretical computer science. So just one topic was fitting for that conference, so I went with theoretical computer science. I'm here today to talk to you about one of my secret passions, which is complexity theory, and I'm going to give you a short introduction to computational complexity. So I'm not going to talk about time or space complexity if you already have an idea what this is. I will use a very made-up real-world example to help you understand what I'm talking about. So let's go. Picture this for a moment. You are volunteering at an animal shelter. The shelter has cats, dogs, turtles, you, and your weird manager. The manager is weird because she sets up arbitrary rules for you and other people to follow. You are in charge of the petting process, overviewing the petting process. So visitors come to your shelter and want to pet animals, and you have to make sure they follow the petting rules. Each rule is different every day. So on your first day, the rule is the visitors cannot pet 2 cats or 2 dogs in a row. They're not allowed to touch the turtles, just for completion, but this is the rule. So visitors come in, and they go pet the animals. They come to you and say, well, I petted a cat, a dog, a cat, and a cat, and you have to decide, for example, if it was a valid petting sequence or not, if they're good visitors or bad visitors. You know, stuff you have to do. You're an engineer, and you're just volunteering there, so after 20 visitors, you think like, ugh, a machine could do this. And so you build one. You start thinking about the process. So let's start out. The visitor comes in and wants to pet an animal, and they can either decide to pet a cat or a dog. If after petting a cat, they pet another cat, they're out. They're bad visitors and they're not allowed to come back. Same with a dog, petting a dog after a dog. But they're good if they pet another animal. This is a very simple machine that can handle your daily task to see if the visitors alternate in petting animals. This machine has a name in theoretical computer science. It's called Finite state automaton. So the pictures with the hand and the animals are so-called states. The arrows between them are so-called transitions between those states. This is a very simplified version of what that is. So if you've never seen anything like this, because you don't have a computer science education, that's basically the rough idea that you just need to follow. So you think you're good, and you're good for a couple of days, but then your manager changes the rule. And they say, well, the visitors first must pet a specific number of cats, and then the same number of dogs. And you sit there, you want to work, but also you want to have time to pet the animals yourself, so you think, well, maybe I can just adjust my machine to do that work of checking the petting sequences for me. And you think about that. So you again start by petting something. If you pet a dog in the beginning, you're out. Bad visitor, bad visitor. But if you pet a cat, you can pet a lot of cats, and then you can switch to a dog and pet a lot of dogs. And if you're in the dog state, you cannot pet a cat again. And you think, yeah, that's nice-ish. I mean, I know now that I can only pet cats before dogs and not alternating between them, but it's not giving me a check for whether I pet the same number of animals. And you think a bit and think, maybe the machine I'm using is just not powerful enough to handle this constraint that the manager gave me. So we're introducing a new part to our machine, and it's called the stack. The stack is really like a stack of books. You can put stuff on top of it, and you can take stuff from the top. That's all it can do. So you cannot grab something from the middle or from the bottom, because it will collapse and will not work. I think, okay, maybe that's already enough. So we go back to our machine, which is not working, and we introduce the stack to it. So whenever we pet a cat, we put a cat token on the stack. And whenever we pet a dog, we remove a cat token from the stack. So if the cats and the dogs are the same number, the stack will be empty in the end. And we're good, it was a good visitor. If there's a cat left, it's a bad visitor. If we want to take away a cat and there's no cat there, although we have petted a dog, then it's also an invalid petting sequence and the visitor is a bad visitor. This machine is called a pushdown automaton. So the pushdown is just pushing stuff on the stack. And the stack is endless. It's like it's a deep cellar with no end. It doesn't matter to you how deep it is. It's just you can use as much as you want. As much of it as you want. Remember that this is just a theoretical model, so like no computer is having infinite space. And again, you're good for a couple of days. But then there's another rule. The rule changes again. So again, we have to pet the same number of cats as dogs, but now introducing the turtles we weren't allowed to touch before. And then thinking again, well, how are we going to handle this with our stack? You know, it's now not just 2 types of animals, but 3, so we just cannot take stuff from the top and put stuff on the top. We somehow have to take into account the turtles. So we need a new formalism, a new mechanism, so we ditch the stack and introduce the tape. A tape is a number of cells. And every cell can be accessed and modified. So in the beginning, we had the stack and we couldn't take stuff out of the middle. We can do this now. We can read each cell, we can modify each cell. The only restriction we have now is saying, okay, the length of the tape is just the number of animals petted. Nothing more. That's it. These are the bounds. Let's see if we can work with that. This tape is a so-called restricted tape. So our input would again be a number of animals, 2 cats, 2 dogs, 2 turtles. I spare you the state transition diagram because it will get confusing starting with this machine. But the idea is the following. So whenever you see a cat, you walk on the tape until to the right until you find a dog, and then until you find a turtle. And then you start again, go back to the beginning of the tape and look for the first cat and go on. So if at the end of the cats there are only X's on the tape, it's a good visitor. If there are animals left, then it's not a good visitor, and they're out. This machine is called a linear restricted Turing machine. A linear restricted Turing machine is the closest we can get to a real computer because we have some restrictions, but a lot of power already. The Turing machine is named after Alan Turing, who was a British mathematician, a math guy. He helped crack the Enigma. Was treated really bad by his government, unfortunately, but he laid the basis for the modern computer, more or less. So that's also why formal models are named after him, because they were basically his ideas. So now, new day, new rule. And the manager is not happy about the process of retrospectively approving the petting process. She tells you, no, you have to check beforehand now if they're going to pet nice or not. But the rule's simple, you know, like, you know what, as long as they stop petting after petting 2,000 animals, we're good, you know. So, okay, weird manager, let's see. Yes, but, you know, you have to check beforehand if they're going to stop at 2,000 animals. So your day starts like this. Welcome to the animal shelter. How are you going to pet today? The first visitor says, like, I'm going to pet 999 cats and 1 dog. And you think about what you do. Yes, that sounds about right. You're just petting under 2,000 animals. You're good. And the next one comes like, I'll pet twice as many pets in the step then in the step before, and I'll start with one cat. And you're already thinking about automizing this, but now you cannot just check sequences of petting, but you have to check, descriptions of petting processes. And that can get really complicated. And the programs are not, like the descriptions are not limited in any way. They can be everything. And you think, well, you have to believe me on that restricted tape won't do anymore. I might need more space. I don't know how many space I will need. Maybe it's twice as much. Maybe it's a lot of orders of magnitude higher than that. So we now go to infinity and beyond. And we introduce an unrestricted tape. And this is the point where it's really just a mental model anymore. Again, we have a tape. We have like the read-write head where we can access and modify every cell. But our tape is infinite, has an infinite amount of cells to both sides. And we can do a lot with it, like really a lot. There's, beyond that, there's basically just, I cannot solve this problem anymore type of problems. Some refer it as a, now what's the German word? It's like a big hammer to solve your problems, even if you just have a tiny, tiny nail. And it's called an unrestricted Turing machine. The description, how you access the cells is not super complicated, but a bit too much for that talk. But you can ask me about that later if you want. So that was the basic introduction of computational complexity. So let's recap a bit. During our process at the animal shelter, our work there, we built 4 machines in our head, mostly. The first one was the finite state automaton, the Pushdown automaton, the linear restricted Turing machine, and the unrestricted Turing machine. These types of machines help to solve so-called decision problems for languages. So what is a decision problem? In English, it would be like decide whether an input is valid against a given set of rules or not. It's still in English, but like a little more computer sciencey is decide whether a word is part of a language. So if you don't have a formal computer science education, you might wonder like what do you mean by what is a language? What is a language? I mean, I speak English, I speak French, and these are languages. But in computer science, a language is just a set of words. Like the set can be finite, it can be infinite. And some sets are described by rules and some are not. So some languages would be, for example, every sentence in the English language. It's a set of strings, it's a set of words. Others would be the set of all valid phone numbers, the set of all palindromes, or the code for every program printing Hello World. So you can see that some of the sets are, no, they are all infinite, as a matter of fact, but just, the set with the word hello is already a language, in a way. And these machines help us to classify those languages. They're formalisms to help us understand how complex a language is in a computational sense. There's some names for those languages. For example, the first type of language we said with the finite state automaton, it's called a regular language. So you might have heard of regular expressions, and they're like really, really deeply connected to that. The Pushdown automata describe context-free languages, which most of the human languages are context-free languages and can be computed with those machines. The next type of languages would be context-sensitive languages. There are human languages who fall into that category. And another one, which you're probably not going to touch anytime soon, are recursively enumerable languages. There are a lot of other words for those groups, but these are some of them. And if you want to look closer into that, you just Google for Chomsky hierarchy. Noam Chomsky was, or is, not sure is it at, he used to work as a linguist at least, and he laid the basis for a lot of formal syntax and formal grammar, and it's a really interesting read because it was one of the first people to look at languages in a mathematical way. And they also laid the basis for this type of theoretical computer science. So now you're wondering, like, why would I need to know that? And maybe you don't. You know, if your job is just increasing conversion by coloring buttons, that's totally fine, and you're probably not going to touch this part of computer science. But it can be useful for validation purposes. As I told you, like, a decision problem is to see whether an input follows a specific set of rules. And like phone number validation or address validation, you might have touched this. And I'll present you with like two groups of problems in this point. So we have the set of valid phone numbers and the valid street addresses. And in the second group, there's correctly matched parentheses and valid SVG. So why would you check for correctly matched parentheses? You probably wouldn't. But if you write a text editor for programmers, for example, that's an interesting thing to know. Like, do you inform your user that they're missing parentheses? And I told you how regular languages are deeply tied to regular expressions. And for a lot of problems and sets we have, regular expressions are totally fine, but for the second group, they're not, for example. Because the second group, the languages in the second group are more complex than the one in the first group. And they need a different type of machine, a different type of formalism to be evaluated and checked against. So you cannot really write irregular expressions for SVG or HTML, for example, because you have the opening and closing parentheses. Now I know that there are people here who probably say, yeah, but there are regular expressions that you can use to do that, and in a way, there are implementations that make it possible, but on a strictly theoretical base, it's not. So, another thing that you might leverage with that, another knowledge that you might leverage is the so-called expressive power. So all formalisms or machines have a power of what they can describe. And one thing this hierarchy has is that the machine in order higher can always be used to describe and solve problems that are lower than it. And a lot of machines and formalisms actually do the same. So we have many tools for one job available. I mentioned that finite state automata, regular expressions, and regular grammars are basically the same. They're not just there's not just a very strong connections, they're so-called equivalent. So you can always transform such an automaton into a grammar or a regex, and the other way around. That's the important thing. So if at one point you think, well, a regex would not help me here, it would be very hard to write, it would be very hard to maintain, you can opt for another implementation of the same formalism and still have the same power attached to it. And there are other tools that are basically formalisms for formal languages like XML schema or JSON schema or tree automata that you might find useful. So for example, you wouldn't implement a finite state automaton by hand, but knowing like, well, JSON schema is more expressive than that. And I like working with JSON schema. You can use JSON schema to handle the task of the finite state automaton. Some people say, well, you should always use the machine, the easiest machine for the job. But it's not really worth losing sleep over how to implement the best machine if your current machine is doing the job. So you're not really losing too much performance or anything if you do it right. And another thing that's really, really helpful, if you know that, is avoiding work. So I'll show you again the rule our manager put last. Padding stops after 2,000 animals. Another rule is now, you know what, as long as they stop padding at any point, we're good. And remember, you have to decide beforehand or not, if they're going to stop or not. And we had the example that they're just going to increase the number of petted animals every step. And just imagining that humans can pet for an infinite amount of time it would be really hard to check if they're going to stop at any point or not. And that's what the machine says as well, like, does not compute. I can, I can decide, I can say so if the petting stops at any point, if it does, but if it does not, I'm not sure, because it could stop in the next step or in the step after that. So if you're able to correctly identify which is the problems, if they're solvable or not, it can help you avoid some work, and then you can just say, I couldn't find an efficient algorithm or an algorithm at all that solved that problem, but neither could those famous people in my surroundings or in history at all. So this is what's computational complexity about. There are different formalisms that describe different sets of languages, and some formalisms are more powerful than others. And knowing how they connect and how they relate to each other can help you make your life a bit easier as a developer. So thank you very much. That was it.